In the summer of 1953, Enrico Fermi, John Pastor, Stanislaw Ulam, and Mary Tsingou conducted computer simulations of a vibrating string with non-linear interactions. Their goal was to explore how energy would distribute among the different vibrational modes of the string over time. 1. The experiment. They used the MANIAC computer at Los Alamos National Laboratory to simulate a one-dimensional chain of particles connected by springs. The springs had non-linear forces, meaning the force was not directly proportional to the displacement, as in Hooke's law for linear springs. 1. They tested different types of non-linearities, quadratic, cubic, and piecewise linear approximations to cubic. Expected outcome. The expectation, based on the equipartition theorem and ergodic hypothesis, was that the energy would eventually spread evenly among all the vibrational modes, leading to thermalization. This means that after a long time, each mode would have roughly the same amount of energy, and the system would behave randomly. 1. Surprising results. However, the results were quite unexpected. Instead of thermalizing, the system exhibited quasi-periodic behavior, where the energy returned to its initial state after some time. This phenomenon is known as the FPUT recurrence. The system did not behave as a typical chaotic system would, and this was a significant surprise to the researchers too. Implications. The FPUT problem challenged the prevailing understanding of statistical mechanics and led to a deeper exploration of nonlinear systems. It showed that not all systems thermalize as expected and that nonlinear interactions can lead to complex behaviors. 1. Legacy. The FPUT problem remains an active area of research, with various theories proposed to explain the observed behavior. It also represents one of the earliest uses of digital computers in mathematical research. 1. Chaos theory. Chaos theory studies systems that are highly sensitive to initial conditions, leading to seemingly random and unpredictable behavior. These systems are deterministic, meaning their future behavior is fully determined by their initial conditions, yet their long-term behavior can be highly complex and appear random. Key concepts in chaos theory include nonlinearity. Small changes in initial conditions can lead to vastly different outcomes. Strange attractors, certain patterns or states that the system tends to evolve towards, even though the path to get there is chaotic. Sensitivity to initial conditions, often referred to as the butterfly effect. This means that small changes in the starting point can lead to very different results. Fermi-Pasta-Ulam-Tsingou, FPUT, problem. The FPUT problem, as previously discussed, involves a one-dimensional chain of particles connected by nonlinear springs. The researchers expected the system to thermalize, distributing energy evenly among all modes, but instead observed quasi-periodic behavior where energy recurred in the initial modes. Connection to chaos theory. The FPUT problem is deeply connected to chaos theory through the following aspects. Nonlinearity. The FPUT problem involves nonlinear interactions between particles. Nonlinearity is a hallmark of chaotic systems and is responsible for the complex behavior observed in the FPUT simulations. Quasi-periodic behavior. The quasi-periodic energy recurrence observed in the FPUT problem is an example of how nonlinear systems can exhibit regular patterns over time. This quasi-periodicity is a precursor to chaotic behavior. Transition to chaos. Subsequent studies of the FPUT problem have shown that by increasing the energy or changing the system parameters, the system can transition from quasi-periodic behavior to fully chaotic behavior. This transition is a key area of study in chaos theory. Exploration of nonlinear dynamics. The FPUT problem was one of the first numerical experiments that highlighted the importance of nonlinear dynamics. It paved the way for further research into chaotic systems and contributed to the development of chaos theory. Modern computational methods. The FPUT problem demonstrated the power of computational methods in exploring complex systems. This has led to the widespread use of computers in studying chaotic systems and nonlinear dynamics. Conclusion. The FPUT problem and chaos theory are intertwined through their exploration of nonlinear systems and complex behavior. The unexpected results of the FPUT problem provided valuable insights into the behavior of nonlinear systems and contributed to the development of chaos theory. Understanding the FPUT problem helps researchers appreciate the intricate dance between order and chaos in nonlinear systems. The KdV equation and the Fermi-Pasta-Ulam-Tsingou FPUT problem are connected through their exploration of nonlinear wave phenomena and solitons. Let's break down this connection in detail. KdV equation. The KdV equation is a nonlinear partial differential equation that describes the propagation of solitary waves, solitons, in a shallow water channel. It is given by plus 6 plus equals 0, where is the wave profile, is the time derivative, is the spatial derivative, and is the third-order spatial derivative. Fermi-Pasta-Ulam-Tsingou FPUT problem. The FPUT problem involves a one-dimensional chain of particles connected by nonlinear springs. The goal was to understand how energy is distributed among the vibrational modes of the chain over time. Connection between KdV equation and FPUT problem. Nonlinear dynamics. Both the FPUT problem and the KdV equation deal with nonlinear dynamics. The FPUT problem involves nonlinear interactions between particles, while the KdV equation describes nonlinear wave propagation. Discovery of solitons. The unexpected results of the FPUT problem led researchers to explore further the nature of nonlinear wave interactions. It was found that the quasi-periodic behavior observed in the FPUT simulations could be explained by the presence of solitons, which are stable, localized wave packets that maintain their shape while traveling. KdV equation as a continuum limit. Researchers, including Norman Zabusky and Martin Kruskal, discovered that in the continuum limit, when the number of particles in the FPUT chain goes to infinity and the distance between them goes to 0, the FPUT system could be approximated by the KdV equation. This connection helped explain the recurrence phenomenon observed in the FPUT problem. Numerical simulations. Numerical simulations of the KdV equation showed the formation and interaction of solitons, which closely resembled the behavior seen in the FPUT problem. This provided a deeper understanding of the nonlinear wave interactions and energy recurrences observed in the FPUT experiments. Integrability and solitons. The KdV equation is an integrable system, meaning it has an infinite number of conserved quantities. This integrability leads to the formation of solitons, which are key to understanding the quasi-periodic behavior in the FPUT problem. The study of the FPUT problem thus provided early insights into the importance of integrable systems in nonlinear dynamics. Summary. The connection between the KdV equation and the FPUT problem lies in their exploration of nonlinear wave phenomena and the discovery of solitons. The FPUT problem's unexpected results led to the development of the KdV equation as a continuum approximation, revealing the role of solitons in nonlinear wave interactions.